Hello everyone, I am Colin Kurz, and this is my report for Lab 5. The purpose of this lab was to find the kinetic friction coefficient of a ball rolling on the ground, and then create a model of the ball's motion and compare it to the real ball's motion. To accomplish this, the motion of the ball was recorded and the data was used to calculate the kinetic friction coefficient. Then, this coefficient was used to help create a model of the ball's motion on GlowScript. Finally, this model was compared to the real video of the ball's motion. The results of this lab show that the model was somewhat accurate to reality. The fundamental physics principle of this lab was Newton's second law of motion. Newton's second law of motion states that the net force acting on a moving object is the product of the object's mass and acceleration. Derived from this law are the velocity update and position update equations, which were used in this lab. The only force involved in this lab was friction force. Some concepts from calculus were also used to calculate velocity and acceleration. To analyze the motion of the object, all that was needed was a lacrosse ball. It was chosen to roll the lacrosse ball on a carpet floor, for the carpet would slow the ball down more than a hard floor and thus make changes in its motion easier to capture and record. It was also chosen to record the ball from the ceiling so that the position of the ball in both the x and y directions on the ground could be recorded. The ball was kicked and its motion was recorded for around a second. The video of the motion was put into Tracker and the position of the mass over time was recorded using Tracker's software. Using the resulting data, graphs of its motion were created. These show a relatively linear decrease in the ball's velocity and somewhat of a right curve in the ball's position over time. The friction coefficient of the object was found by using the recorded data to calculate the average magnitude of acceleration for the object. Next, the normal force was found. Since the ground was flat, the normal force had to have the same magnitude as the force of gravity. Then, the net force acting on the object was found by multiplying the average acceleration found earlier by the mass of the object. Finally, settling the magnitude of the net force equal to the friction coefficient times the magnitude of the normal force, the friction coefficient was calculated. It was found to be 0.260. The computation of the motion of the object was created by finding the friction force and then using that to update the object's velocity and position. The friction force was found by multiplying the magnitude of the friction force by the unit vector of the force. This unit vector was just the reverse of the unit vector of the velocity because friction acts in the opposite direction to the motion of an object. The unit vector was updated with the new velocity for each iteration of the loop to ensure that it would be pointing in the right direction. Something of note is that the initial velocity used was actually the average of the first five velocities recorded. This was done because of the inconsistent nature of the data, which may have caused an extreme and inaccurate initial velocity of the ball if only the first velocity recorded was used. Overall, the model accurately predicted the magnitude of the ball's velocity. It predicted that the ball would slow more than was observed, but it overall stuck close to the real data points. On the other hand, the model was not very accurate in predicting the position of the ball in 2D space. The model predicted that the ball would stay mostly along a linear path rather than take a right turn like the real ball did. This is likely the result of some error in the lab process. It may be because the direction of the spin of the ball was not accounted for, which may have caused it to move in the y direction more than was expected. It may have also been because of the rough nature of the carpet, which might have unexpectedly pushed the ball in one particular direction. Both of these possibilities are supported by the fact that the ball moved very slightly in the positive y direction initially before going in the negative y direction. One remaining question is, what if the ball had been rolled on a floor with less friction? For starters, the velocity versus time graph would have likely been flatter, for a smaller friction force would have meant that the ball would have slowed down at a decreased rate. This would have also caused the ball to roll further. Finally, the x and y position graph would have also changed, but it is hard to tell in which direction. The lower friction could have caused the ball to spin more and thus go further in the y direction, but the less coarse floor also means that the ball would not have been unexpectedly pushed in one direction, so it could have also gone less in the y direction. Overall, it's very hard to say if the ball would have gone further or not as far in the y direction on a smooth floor. Thank you for listening.